Hello again, this is Daryl here. I want to demonstrate using an ATmega 328 microcontroller to configure two PWM outputs for servo motors. And we'll use a 16-bit timer 1 so we get the higher resolution on the positioning in the servo motors. So for now, we just want to configure the timer 1 for the two PWM outputs. And we'll use OC1A and OC1B pins, which you can see on the picture here. They're on pin number 16 is OC1B, pin number 15 is OC1A. So we'll have to configure those pins as output pins. We'll do that at the beginning of the program. And then we'll set up the pulse width modulation or the output compare register values so that we have a period of 20,000 microseconds, which is 20 milliseconds. That's the appropriate frequency of 50 hertz, 50 updates per second for the servo motor. So we'll do 20 milliseconds, which is 20,000 microseconds for the frequency, and we'll use the input capture register to control the frequency. So it will count from 0 up to the value stored in the input capture register and then reset to 0 and start up again. Then we'll use the OCR1A and OCR1B, both of those registers, to configure the pulse width modulation signal's pulse width output. So when the counter starts at 0, the pulse will go high. Then when it has a compare match with OCR1A or OCR1B, the corresponding pin signal will go low, and then it will continue counting up until the other OCR1A or OCR1B pin has a compare match, and then that pin will go low, and then it continues counting up until it has a compare match with the input capture register. When that happens, the counter will reset to 0, and when it resets to 0, the signal on both OCR1A and OCR1B, OC1A, OC1B pins will go high when it resets to 0. And then it will repeat the same cycle over and over again. So what we want to do is we'll start by setting the output pins on PB1 and PB2 to output for our signals. Then we'll set the, because we have a 16-bit register timer 1, it can count up to 65,535 before it resets. And we only need it to count up to 20,000 microseconds. So what that means is we can use the CPU clock and divide it by 1, and then we'll put the value 20,000 in the input capture register, high and low byte. And then we'll start off with the value that's about center on the servo motor, which will be about 1,500 microseconds, 1.5 milliseconds. And that will center the servo motor. So we'll start with that. And then we'll see how we're doing on time on this video, if we have time to finish all that. And later, when we do the analog to digital conversion, we'll take the analog input from a potentiometer, convert it to digital, and use it to control the pulse width on the OC1A and OC1B pins. So we could have two potentiometers controlling two different servo motors. But to get started, we know we need to use PV1 and PV2 for OC1A and OC1B. So let's go to the AVR Studio and create a new project. And I'm going to call this timer 1, so T1 PWM. T1 PWM. I'm in my ATmel projects folder, you can see here. And I have create folder and create initial file set. So it's going to create a folder and put the files in it. And we'll use the ATmega 328 ATmega 328P. And if everything worked right, you see all the registers on the right hand side, and we'll maximize our window. And so normally we want to put a description, maybe username, on PB1 and PB2 timer 1. Okay. And a dot. We want to include our file so we can use the register name. So dot include m328pdef.inc .org. Oh wait, let's define some registers. Temp equals our 16, and we'll go ahead and define registers high and low bytes for PWM-A and PWM-B for the two different PWM signals. And we can use registers like 15 and 14 for PWM-A, for example, and then 13 and 12 for PWM-B. So I want to define that the register names for those. So PWM-A H, the high byte, equals R, let's say 15, and PWM-A low byte equals R 14. PWM-B high byte equals R 13, and yes, that's right. PWM-B low byte equals R 12. Okay, so we'll come back and define more registers if we need them later. For now, let's just get started with a .org, the reset vector. And that's always at address 0000. And we're going to use a interrupt. Every 20 milliseconds we'll update the register value for the OCR1A and OCR1B. There's no point in doing it more often than 20 milliseconds because that's how fast we update the servo motor position. And we'll use the interrupt capture register will be set to 20,000 microseconds, 20 milliseconds. And if we set the timer overflow interrupt, when the counter counts up to the interrupt capture register, and it will overflow and reset to 0 at that point, provided we have the waveform generation mode configured properly. When the overflow happens on the interrupt capture register, it will trigger an overflow interrupt. So for now, we can do a .org and OVF1 ADDR, and we will use that to toggle or update the OCR1A and OCR1B values to update the pulse width on the servo motors. So I'm going to call it PWM update for now. So we'll do our jump to that to PWM update. And then .org int underscore okay, so interrupt vector size, that's going to move our first instruction on the program down below the space used by the interrupt vectors. So I always start with the stack pointer configuration. And we'll put it at the RAM end. And I'll learn to type. There we go. So this is a high byte for the stack pointer. And the low byte for the stack pointer. Now we'll configure port PB1 and PB2. Those are the OC1B and OC1A pins. So we'll configure those as outputs. And because it's just 2 pins, we could either load a value into temp and then output it to the data direction register, or we could do a SBI DDRB, PB1 and SBI DDRB, PB2. So that sets the data direction register bits for those 2 pins. And now we need to set the output compare registers. We could do that first if we want to. And because those are 16-bit registers, you have to write the high byte first and then the low byte to configure them. Otherwise, the transfer from the buffer in the timer doesn't happen. So on the second write instruction, which meaning if you wrote the low byte and then the high byte, after you write the high byte, it's waiting for the low byte to be written, so it transfers the high byte and low byte together at the same time. So we're going to write the high byte to the OCR1A, OCR1B, and the input capture registers. So we'll write the high byte and then the low byte in that order on each of those. So let's start with the frequency. The period of our signal is going to be 20,000 microseconds, 20 milliseconds. So we want to do the LDI, the high byte of 20,000. And of course that needs to go to temp. And then output that to, whoops, remember we're on ATmega 328. And the timer 1 registers have no I/O address, so we can't use the output instruction. We have to use the STS instruction. So STS ICRH, temp. And then we do the low byte. So that does the input capture register. That will set the period of time for each cycle. Now we can set a default starting point for the OCR1A and OCR1B as 1500. In fact, what we could do is name the values 1500 and our minimum PWM value and our maximum PWM value. We can name those or define names for those up at the top of our program. So we're going to be way out of time before we finish this configuration. We'll have to make this another part, right? Okay, so LDI, let's do the basic neutral or center position in the servo. So the center position is approximately 1500 microseconds. So I want the high byte of 1500 to go to both OCR1A and OCR1B high bytes. So out, no, STS, because OCR1A and OCR1B have no I/O address. So OCR1AH, then I can also do it at the same time. OCR1BH. Okay, we're running out of time. We're going to have to continue on the second part of this video. And then, so we'll be back.